So today's topic is on electron configurations. Like I said yesterday, these are using three of the four quantum numbers to describe where in the atom you can find electrons according to their energy level, the shape of the orbital, and the orientation of that orbital. So I'm going to go over, there's three basic rules that we follow when we're assigning electron configurations, but the most important thing I'm going to show you today is how to use the periodic table to write the configuration. So a lot of the rules you don't really need to remember as long as you understand how to apply the periodic table. All righty. So the quantum model of the atom is better than the Bohr model because it describes the arrangements of electrons and atoms other than hydrogen. Remember that Bohr's model only applied to the hydrogen atom with one electron, but the problem is that, of course, any other element besides hydrogen has more than one electron. So we need a model to be able to describe the other, 117 elements on the periodic table. So electron configuration just refers to the arrangement of electrons in an atom. And because atoms of different elements have different numbers of electrons, the electron configuration for each element is unique. Now, the first thing that I want to point out is why atoms of different elements have unique electron configurations based on the fact that they have different numbers of electrons. So why is that? Because atoms are identified by their atomic number. Does anybody remember what atomic number represents? It's the number of, oh, there he is. Oh, gonna let him in or not? Am I going to be able to, there, wait, no, sorry. There we go. Okay. Okay, so does anybody remember what atomic number represents? The number of, anybody? Bueller.
Number of atoms in a, what do you call it?
It's not the number of atoms.
Proton.
There you go.
There we go.
Yeah, protons. So atomic number is the number of protons. If you look at a periodic table, it is organized, and I don't know why I don't have a paper copy of one here at home, I guess because everything's digital now. But all of the elements are organized according to their atomic number, starting with hydrogen number 1 and helium, lithium, beryllium, blah, blah, blah. No, you don't have to remember the periodic table. Why? Because why would you have to? Because you have it as a tool. It's like having a math teacher say you can't use a calculator. Well, why? Like, is your math teacher testing your arithmetic skills or your math skills and being able to manipulate numbers and variables? So I look at it as, even if you think like you love chemistry and you want to have a career like as a chemical engineer or whatever, you're not going to go into your first day on the job as a chemist and have your boss walk up to you and say, quick, what's element number 23? Because the periodic table is a tool, just like a calculator and everything else. You always have tools in real life, unlike in school where for some reason we teach you that you just have to memorize all of this crap and then like vomit it back on a test and then, yay, you're smart, congratulations, you pass. I would rather you be able to use the tools that are available to you in order to explain these concepts. So that's why I'd like to focus more on the periodic table and how to use the periodic table to write the configurations. So back to my point. See, I told you I go off on tangents. My point, why, oops, I'm on the wrong slide. My goodness, my bad. Oh my God, I just passed it again. Let's see if I can do this time. Okay, there we go. Different numbers of electrons. Why do atoms have different numbers of electrons? Is because in an atom, because an atom is electrically neutral. Excuse me, I just ate lunch. That means that the number of protons has to equal the number of electrons because protons are positive. That's a terrible positive. And electrons are negative. So if you have something that as a whole is a neutral entity or a neutral thing, and it doesn't have an electric charge, but it's made of things inside that have charges, plus and minus charges, what makes it overall neutral is the fact that protons and electrons are equal. Now, because every element has a unique number of protons, that means that every element as an atom, as a neutral atom, has a unique number of electrons as well. So every single element in the periodic table has its very own personal electron configuration. Okay, back to this slide. So when we write electron configurations, it's always assumed that this configuration is the ground state. If you remember the ground state, which is the lowest possible energy when all of the electrons are at their lowest energy level. Okay, just said that. And like I said, there's 3 rules, which I'll go over. But I'll say in theory, it's important, I guess, to understand the rules and how they apply to writing electron configurations. But in practice, they don't matter. Yeah. And as an educator, I will always be honest with you and tell you like whether things are important or useful or whatever. So academically, like test wise and doing homework and things like that, yes, they're going to ask you if you understand the difference between these 3 rules and why they are important in determining configurations. But in practice, like when you apply it, what do you call that? Realistically, they don't matter because you use the periodic table, which is why I like doing that instead. So the way that electrons are arranged in any kind of element is that you always fill the lowest energy levels first. So this is going to be part of what's called the Aufbau principle. The Aufbau principle is going to explain the order in which you fill the orbitals, starting with the lowest energy level. And then even between the S, the P, the D, and the F, remember the shapes from yesterday, those are going to be filled in a specific way as well. Then we have the Pauli exclusion principle and Hund's rule. And the reason why I'm honest with you and I tell you like in reality, like in the real world, the rules don't matter if you know how to use periodic table to write configurations. I've been teaching this subject for 18 years and I still get these 2 mixed up. I don't know why. Every single year, I'm always like, which one is which now? I can't remember. And then every single year, you would think after 18 years it would stick, but yeah, it just doesn't. So because you don't practice it on a regular basis for these 3 rules. So like I said, Aufbau is showing you the order that you occupy orbitals. And you're always going to fill, like I said, the lowest orbital that has room for an electron first. So remembering that each orbital can only hold a maximum of 2 electrons. Once the lowest orbital is full with 2, then you go to the next lowest and so on. Now, this is the chart that they give you in the textbook. And I think this is absolutely useless because it's like, first of all, it's like 2 different parts. So you've got all of these boxes and I'm like, I don't even know what I'm looking at. Like, what is that? But then the easier thing would be just to go up this line in order because it's like it says up in energy. So you would start at the bottom with 1s and then go to 2s, 2p, 3s, 3p, 4s, 3d, whatever. So there is a trick that I've seen that I've seen a lot in Thailand. And I'm trying to see if I can remember. So it starts off like this, 1s, and then because level 1 only has the s orbital, and energy level 2 has 2s and 2p. Then you have 3s, 3p, 3d, 4s, 4p, 4d, 4f, and then 5s, 5p, 5d. I'm going to run out of a room here, but it doesn't matter. And then basically what they do is they come along and they say, okay, so I'm going to draw an arrow through these levels in the order that you fill them. So it goes something like this. Something like this, and then around like that, and then like that, something like this. I'm messing it up because I didn't draw it very nicely, but something like that. And if you've ever seen that picture before, I want you to ignore that too, because that's also just hot mess. Like, why would you have to remember something extra if you're always going to have a periodic table in front of you to be able to use? And for my class, of course, you will always have, well, with we were actually learning in person, you would always have a periodic table to refer to, always. So what I want to show you instead is how to use the periodic table to understand the order to fill the orbitals. And this is where the magic happens. So let me share, oops. Let me get out of here first. No, don't beep at me. All right, no. All right, get out of here first. The joys of Zoom teaching. Okay, I don't want to be in there. I want to be, all right, here first, just to review what I talked about yesterday. And again, everything that I went over yesterday with the quantum numbers and the principal energy level N and angular momentum quantum number L, which is equal to 0 and all of the integers up to n-1, and then angular, I did that already. Magnetic quantum number, which is lowercase m, and the values for m are negative L through to L, and how that corresponds to SPDF, right? Understanding the quantum numbers that came from Schrodinger's equation, and then how he came up with the quantum numbers based on all that really complicated math crap, and then how that leads to the fact that you've got this, the periodic table, you've got 4 blocks, and it's not an accident that it's set up this way. Now, the first thing that I want to point out is that I have, no, that's the wrong one. Is it? Which one do I use? That one. I have blocked out LA and AC because they're part of the D block. That's why you see them. Nope. Oh, well, that doesn't matter. That's why you see them up here, because they actually belong in group 3, period 6 and 7. So they don't actually belong on the bottom. Anywho, oh no, didn't mean to erase all of that. Was it yellow? Highlighter, yellow. Okay. So based on the quantum numbers, we know that there is only one s orbital, right? Because the angular momentum quantum number L equals 0 is s, that represents s. And you can't have -0, +0. So there is only one s orbital, and that one orbital can only hold 2 electrons. So you see the entire groups 1 and 2, that makes up the s block, okay? So there's only 2 elements per period or per energy level, because remember all the periods on the side, 1, 2, 3, 4, 5, 6, 7, that represents principal quantum number. Then you have the P block, which they're also called these the main group elements. And there are 3 P orbitals for a total of 6 electrons. So 13, 14, 15, 16, 17, 18, that's 6 groups, right? So 6 elements per energy level or per period for the P block. Also want to point out that helium, even though it's in group 18, is the second element that is in the S block, but it's in group 18 because it is a noble gas. Then we have the D block. Remember, there are 5 D orbitals. Each one can hold 2 electrons for a total of 10. So there are 10 elements in each level for the D block. And then finally F, there are 7 orbitals for F. Each one can hold 2 for a total of 14. So you have 14 elements in the F block. Okay, so just remember these blocks. Now, I told you you could ignore the rules because all you need is this. So here it is. The way that you fill the orbitals or you're following Aufbau's principle, rather than remembering charts or graphs or squiggly lines or whatever, just use the periodic table and fill the electrons in order on the periodic table. If you understand that this represents the principal quantum number, and if you understand the 4 blocks, you literally just go in order. So if I ask you the configuration for hydrogen, hydrogen is the first element, and it is in period 1. It is in the S block, and it has 1 electron. So its configuration is 1, because remember, we use a principal quantum number first, followed by the shape of the orbital, and then we use a superscript to indicate how many electrons are in that orbital. So we have 1, it's in the S block, so 1s, and how many electrons are in it? 1, your superscript. There's your configuration. Okay, so you start with the lowest level. For Aufbau, of course, like I said, you can look at the chart in the book and be like, meh, why would I bother memorizing that if I just use the periodic table and I start at number 1? And then once number 1 is full, so for example, let's go crazy and let's do sulfur, right? So identify where your element is first, and then just fill the orbitals in order, as long as you understand the period number is equal to the energy level and you identify the blocks that they're in. So let me just go ahead and erase that first. Okay, so if we want sulfur, I'm still going to start with hydrogen, and I'm going to fill the orbitals until I get to sulfur. So I'm going to start with 1s2. So that takes care of hydrogen and helium. That's full. That's the first energy level. After helium, I go to lithium. Where's lithium? It's in period 2. So we're now in energy level 2. What block is this? This is the S block. So if I do 2s2, that covers up to here. Then I need to go all the way through boron to neon. It's still level 2 because we're still in period 2. But now I'm in the P block, right? This is the P block here. So I fill up all the way through neon. So I fill in 1, 2, 3, 4, 5, 6 electrons in the P block to P6. That gets me to neon. After neon, I go to period 3. So we're now in energy level 3. We fill in 3s first, 3s2. And then I go all the way up to and including sulfur. So I'm in 3. Now I'm in the P block, 3p. Oh, let me erase the scribble so we can see. So I'm in 3p, and then I go 1, 2, 3, 4. 3p, 4. Ta-da! Applause, applause, applause. Yay. So you see how much easier that is than having to remember like this, whatever that whole trick is, or like going to Aufbau and having to remember that weird chart with boxes, which I don't even understand. It just overly complicates everything. Super easy, because like I said, you will always have a periodic table to reference. And as long as you understand, well, that's really annoying too. Can I just do that? Yeah, easier. As long as you understand how to use the periodic table and you learn in your mind that period number is equal to the principal quantum number. So that comes first. And then I've got my S block, my D block, my P block, and my F block. And you just follow atomic number. Now things get tricky because of course they do. So 2 things, actually 3 things, maybe 4, I don't know. First thing, when you get to the D block, the principal quantum number for the D block is equal to n-1. So when you get to period 4 and you fill up calcium, so filling up calcium, you would start, like, let's just say that we filled all that in already. You get to calcium, that would be 4s2, right? With all of the other stuff in front of it, because you have to fill it from the beginning. Once you get to scandium, that's in the D block. So even though we're in period 4, we go down to level 3 because the D block elements, their energy level is N minus 1. So scandium would be 3D1. Okay. Now, second thing, because I told you there's 3, maybe 4 things. Second thing is the F block. The F block is equal to N minus 2. So the F block is in period 6 and period 7, but they're going to be 4F and 5F, N minus 2. Next thing, number 3, and don't worry, we're going to be doing tons of practice with this so that you'll get quite used to it. The hardest part, I think, for you guys at the moment is if I give you an element, you're going to spend like more time trying to find the element on the periodic table than you actually will filling out the electron configuration. Right, so thing number 3, I want you to make sure that you are going in order of atomic number. And the reason why I say that is when you get to barium, okay? Can I zoom? Yeah. When you get to barium, it's important that you recognize the fact that going to the next element, it tells you 57 to 71, and that takes you down here. So once you get to barium, you go down here and you fill in this, group. So you go all the way through to, what is it, lutetium. Then once you get to number 71, you come back up here to 72, okay? That's why I said follow the atomic number. If you do that and you remember your S, D, P, and F blocks, and you remember that principal quantum number is period number, remembering that D is N minus 1, F is N minus 2, you can't go wrong if you just understand how to apply that. Okay, so what I want to do is I'm going to pick out some random elements and I will go through how to assign the electron configuration with you. After that, I'll give you a couple of elements and I'll have you try it on your own. So how about this? How about one of you guys give me an element to do and I'll show you how to do it. Anyone? Any element at all?
Potassium.
Which one?
Potassium.
Potassium. Okay, cool. Potassium. So you start with finding where the element is and say, okay, that's the end point. That's the end of the race, right? Like when you do a race and you have a starting point and an end point. Potassium is my end point. My starting point is always hydrogen, and I fill them in order. So I start with 1s2. So I got 1s1, 1s2. The next one is 2s2. That gets me to beryllium. Then I do 2, this is the P block, and there are 6 elements, 2p6. Then the next 2 elements are 3s. There's 2 of them. I go all the way through 3p, that's 6. And my last one is 4. It's in the S block, and there's only 1 of them. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Ta-da! That was easy. Give me a hard one. Anybody? Okay, I'll pick one. Einsteinium. We're going for the gold since it's the Olympics anyway. Go for the gold, like almost all the way at the end. Okay. This is going to be a long one, so buckle up. Again, start with hydrogen. Fill in 1s first. 1s2. I'm going to write at the top because it's going to be super long. 1s2, hydrogen, helium, done. Next, 2s2. Full, done. Next, these guys, 2p6. Next, 3s2. The next one, 3p6. See how I'm just going in order? Following period number, which is principal quantum number, 4. Fill in the s orbital. There's 2 of them. Now here's where we get a little difficult. The next one, remember, D block is n-1. So all of these guys, all the way up through zinc, is 3d10. Clean that up. 3d10, because there are 10 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 3d10. Then we go back to P, which is just N. So we go back to 4, 4P, excuse me, 4P6. That gets me to krypton. Then I'm here, that's 5s, 5s is 2. I go back to the D block, so I go back down to 4, or not back down, but I go down to 4 because D is -1. So that's 4D10. Then I'm back in P, so I go back up to 5, 5P6. Then here I've got 6s. There's 2 of them. Now, remember what I told you when you get to lanthanium. Lanthanium is the element that belongs right here in this spot. So that's why I cross these 2 out on this periodic table. There's a reason why I like this periodic table, mostly because it has the oxidation states in the top right corner, which you don't have to worry about yet, but you will eventually. So once I fill in barium, then I am going to go down to cerium. Now, you might think, well, aren't you skipping number 57? Because technically I'm going from 56 to 57. Well, yes, but here's the thing. I'm going to go all through here to here until I get to there. So lanthanium is going to be included in the end anyway. It's going to be included when I do 5D. When I get to the Einsteinium group, then I will explain why it's different if you don't go all the way through the F block. So from 6s2 is where we ended up. So I've done barium. Then I come down here, and this is 4F, because remember we're in period 6, but F is n-2. So we're in 4F, and there's 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So then I've filled all the way through lutetium. Then I'm going to come back to number 57, and that's going to be 5D10. That gets me through to mercury. Then I go to the P block, back up to 6, 6P6. Then I go to the last S group, which is 7s2. Now here's the difference. Because I'm going to go like in the middle of 5F. Because the, let me change colors here. Let's do pink. I like pink. These 2 groups actually occur right here in this pink area. So if you could actually separate the LA and the HF and you could make room for this entire block, they would fit right there. So technically, we have to do, what's the name of it? I know it's probably actinium. Yeah. Okay, so I got to do actinium first because this is the element that belongs here in that spot. Because I'm not going to come back to the rest of that D block. So I have to account for actinium first because it's number 70, what? No, 89. It's number 89. So I go from 88 to 89 only because I'm not coming back to Rutherfordium, which is 104. So I have to write, ooh, that's a bit small, isn't it? So I have to account for actinium first. So that is, that's in period 7, the D block. So that is 6D, D1. So that's actinium. Then I go down to thorium and I go to einsteinium, which is 5F. And then I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5F10. And that is the whole electron configuration for einsteinium. So it seems tedious, and you might be thinking, oh dear God, but it's literally going to be the same thing over and over and over again, because you're always starting with hydrogen and you're just filling. You're filling in from the period and the block, period and block, period and block. That's it. All right, we have 13 minutes. So I'm going to give you, I'll start with one example. I want, let's say iron. I want the configuration for iron. And I'll give you 3 minutes. And I'll come back. Well, I'll still be here, but I'm going to mute myself. I will talk to you again in 3 minutes at 12:11. Okay. So again, starting with hydrogen, we fill 1s2, done. 2s2, done. 2p6, done. 3s2, 3p6, 4s2, and then 3d, 1, 2, 3, 4, 5, 6, 3d6. Yep. Yeah. Okay, before I go, I have to cover the other two rules just because, you know, I don't know, I guess because that's the rules or something. All right, so we did Aufbau, blah, blah. Oh, that reminds me. Since, let me get rid of that. Oh, wait, I need that. Okay, so just coming back to the Aufbau principle, remember that I said that the D block is n-1 and the F block is n-2. This reflects that because you see we go from 1s, 2s, 2p, 3s, 3p, 4s, 3d, right? 3d is slightly more energy than 4s, but less energy than 4p. So this is how Aufbau categorized it. And then you got 5s, 4d, blah, 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 blah. But like I said, since the beginning, I would much rather show you how that works according to the periodic table. You just go in order, and then you can come back and say, oh yeah, okay, now I see that's like that Aufbau organized the orbitals that way. I don't know why that's covering up the text, but anyway, okay, blah. Rule number 2. The second rule is called the Pauli exclusion principle, and it reflects the importance of the spin quantum number, the one that I told you that was either +1/2 or -1/2. It reflects the fact that no two elements have exactly the same no two electrons have exactly the same 4 quantum numbers, because even though each orbital holds 2 electrons, for example, if you have like the 4s orbital and you've got two electrons in there, they cannot have the same 4 numbers. So you'll have 4s, and then one of them will have a +1/2 and the other one will have a -1/2. And like I said before, it doesn't have any application, I guess, like as far as writing configurations goes, you don't ever see it. But that means, like I said, no 2 electrons in the same atom can have the same set of 4 quantum numbers. Now, I usually skip this. This is called orbital notation, mostly because I find it extremely tedious, meaning it takes a really long time to do, and it's not very useful, but it does have one use, and that is explaining, obviously, Pauli exclusion principle, but also there's some exceptions for electron configurations when it comes to the D block, and then you come back to Pauli exclusion principle to explain why. So the arrow going up, if I can draw a circle properly, the arrow going up and the arrow going down reflect the opposite spins of the electrons. So orbital notation is basically just writing a line, and then for each orbital, I mean, putting one arrow up and one arrow down to indicate the spins. So 1s would be like this. If you had, let's say, an element with 12 electrons, so you don't even need to know the identity, you just need to know the number of electrons. So if I give you, one more time, if I give you 12 electrons and then I ask you to do the orbital notation, you just fill in the orbitals in the same order. The only difference is when you get to the next orbital, which is P, there are 3 orbitals, so you have to do 3 lines. So of 12 electrons, you've got 2, 4. And then this is going to, I'll just show you Hund's rule, which is the next rule, but I'll just explain it here. Hund's rule applies to the P, D, and F orbitals. And it basically says that the way that you fill electrons in orbitals that have different orientations is that you fill in each orbital with a single electron all going in the same direction before you go back and pair them up. So this configuration has a lower energy profile than if I do 2s 2p. Then if I, let's say I've got 3 electrons in 2p, having each of them, having 1 electron in each of the p orbitals has a lower energy than doing like 1 up, 1 down, and then 1 up, and leaving the third one empty. So you've got 1 orbital, 1 p orbital that's full, 1 that's half full, and 1 that's empty. That's going to create a bit of a higher energy state. And like I'm sure I've mentioned it to you guys, but I will always mention it in all my, like all the subjects that I teach, is that the universe likes to have as low of energy as possible. The universe is super chill. So this, you don't do that. That's called Hund's rule, right? So you go like up, 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 and then down, 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 instead of going up, down, up, down. That's going to account for the exceptions, which I can't talk about because I'm out of time.